Hello everyone. The today's topic is about voltage source inverter fed induction motor drive. The definition of voltage source inverter in voltage source inverter is that. So if it is looked up about these terminals, these three terminals of output of the inverter, these should be act like a voltage sources. Then we call this entire inverter is a voltage source inverter. If it is viewed at the output of the inverter, this inverter terminal should act as a voltage sources. This is giving a definition of voltage source inverter. Now, what is the necessity of voltage source inverter for induction motor drive here? So, how it is going to be operating an induction motor, how it is going to be controlling an induction motor, we will see in this topic. And this topic is completely based on the V by F control operation. Just how the V by F control is achieved and how the operation is done, we've seen equations and characteristics in previous classes, and in now the current class is going to be describing a physical model, means that a static means by using a converter how we can achieve the real-time V by F control. We will see in this topic. So here my intention is to control this induction motor with variable voltage, variable frequency. These three terminals will act as variable voltages and variable frequency terminals. So this is achieved now by using this VSA fed induction motor. So generally this entire operation and switching sequence, switching pattern is not needed to describe here, because my concentration is on to control the induction motor. It is not to say the operation of the induction this converter. So that I am concentrating on the control of induction motor. So I am moving for that now. Before going for the complete operation of this induction motor under V by F control, let me explain the modes of operation of this inverter. This inverter can conveniently operate in two modes, that is 180-degree mode and 120-degree mode. The most probably will prefer 180-degree mode operation. So here in this explanation also I am using that 180-degree mode operation. And it can be again operate in two ways, either in PWM inverter mode or in stepped wave inverter mode. These ways of operation is depending upon the type of pulses we are provided for these devices, switching devices. So what type of pulse I am providing? Either it is pulse width modulated pulse generation or a constant firing angle pulse generation. Depending upon the way of pulse generation to the devices, this inverter will operate in two ways. One is in for pulse width modulated inverter and stepped wave inverter. So then what is the difference of these two inverters, stepped wave inverter and pulse width modulated inverter in the sense? You must keep remember this, carefully listen. A stepped wave inverter will having possibility to control its frequency internally. Means that it only controls the frequency, it cannot control any voltage or current magnitudes inside the inverter. So that if you want to control, if you want to regulate the voltage and current quantities, you need external means. External voltage control is required, external current control is required for stepped wave inverter. Whereas it comes to the PWM inverter will have the function to control both voltage and frequency internally in the converter. There is no external converters are required. These two you need to keep remember before moving to the topic. So this is the waveform representing the stepped wave inverter. This stepped wave inverter we also called as a 6-step inverter. This I am plotting for one line voltage. This is RY, R and Y phases. Between these two I am measuring the voltage. So the one line voltage waveform I plotted. And its firing angle is also given as pi by 6. Here already we have a 6 thyristors. So 6 devices will be having 60 degrees of each conduction. So that pi by 6 to 5 pi by 6. So we'll be having 60 degrees here the conduction. So here also the negative half cycle is also will be having 60 degrees of conduction. This is a symmetry waveform. So if you take average for entire thing, that will become 0. So that we are taking average of average value for only for half cycle. So this half cycle average output voltage magnitude is constant, I said. Why? Because why magnitude is constant in the sense it is having a waveform from pi by 6 to 5 pi by 6. If you measure here the magnitude for this from pi by 6 to 5 pi by 6, it is giving only one particular value that is constant. So the magnitude cannot be varied in the 6-step inverter mode of operation. This is the model waveform that it can be produced once you are operating voltage source inverter as a 6-step inverter. And this is also a line voltage, one line voltage. Similarly, we have all the line voltages and they are also having their waveforms by 120 phase shift each. So based on this, you can conclude that the voltage magnitude cannot be controlled. It is a fixed quantity. Average you are taken from here to here. And you can vary the frequency of this by adjusting the time period. The time period, it is having a waveform is having a time period for a full cycle. It is a 2 pi. You can regulate this value of 2 pi whenever you require. Then once your time period is varied, then the frequency of the inverter is varied. By seeing this waveform, we can say that the 6-step inverter can vary the frequency, but not the voltage magnitude. So here, this process is explained here in 6-step inverter VSI based control. Now we have two things here. Sometimes I may be avail a DC supply. Sometimes I may be avail AC supply with me. What happens if it is DC supply is available? What happens if it is AC supply is available? How the circuit scheme is going to be modified? We'll see in this. So my requirement, I'm saying, my requirement is that I need to have variable voltage, variable frequency here at the output of the inverter. Here also variable voltage, variable frequency. So this variable voltage, variable frequency should maintain V by F ratio is constant to operate the induction motor with constant maximum torque. That I need to get here from the output of the inverter. As we discussed as of now, the 6-step inverter is not capable of adjust the voltage. It cannot able to control the voltage. Only frequency it can control. Then how I can control the voltage here in the sense for that in the input of the inverter itself we are providing control voltage. Once it is controlled voltage, obviously the output is also a controlled voltage. So how we are getting a control voltage here in the sense directly I cannot get because I am having a fixed DC supply here. And that fixed DC supply I'm not directly connecting because I required here is variable DC. To get variable DC from fixed DC, we are using chopper. So here external voltage control is done in the chopper circuit. Now I am processing this fixed DC supply through this DC chopper and it produces the output as a variable DC and it is processed through a LC filter. The function of LC filter is here to ripple out or remove the ripples in the output of converter. This DC chopper will produce a pulsating DC. This pulsating DC is processed through a filter and all the ripples are removed, and this variable DC what it is produced is connecting across this DC input to the 6-step inverter. So that now the input is become variable DC. So then you can get continuously the variable DC by adjusting the duty cycle of this chopper, and you can have variable DC. That variable DC externally is controlled, and the output terminals of the inverter is also looks like a variable AC, because the input itself AC a variable, and output is also a variable quantity. And frequency of this output can be controlled internally by adjusting the time period of the 6-step inverter based on the voltage magnitudes what we controlled here, because it is proportionally has to vary voltage and frequencies so that the V by F ratio remains constant. So this scheme explained for when DC supply is available. Suppose 3-phase AC is available for me, then what I needed to do. The same circuit, only the chopper is replaced with the control rectifier, and DC supply is with the 3-phase AC supply. And here also I need to get the value of variable voltage and variable frequency. So for that, the 6-step inverter cannot control the voltage, so that external voltage control is required. Means that at the input of the inverter we need to have control voltage. This control voltage I am getting from some other converter. The type of converter here it is decides the type of input is available. If suppose a 3-phase AC is available with me, hence I need to use the control rectifier. A rectifier can convert AC into DC, so that I am using here the control rectifier. 3-phase AC I am converting into variable DC. It is again processed through a filter because it is a pulsating DC here. So it is processed through a filter, and after that we'll be having variable voltage after rippling out this converted voltage. Now this variable voltage is fed as input to the 6-step inverter. The output voltage is also controlled by means of variable input voltage. Then the frequency internally controlled, variable voltage, variable frequency is obtained at this terminal. So I can able to control the induction motor here under constant V by F control. This is when this inverter will operate in 6-step inverter mode. Means that providing direct firing angles instead of pulse width modulated control. Once you are giving a pulse width modulated inputs to the gates of these devices, then what it is happens we will see now. So this is when that inverter, voltage source inverter, will operate in pulse width modulated inverter. So you can compare these two now. This is the pulse. Previously it's produced, a single pulse is produced, and if you take the average value of this, it is constant. And if I now will be having like this, this is also a half cycle, first half cycle. This is pi by 6 to pi by 6 to 5 pi by 6. So like this, pi by 6 to 5 pi by 6. The similar control it is also is there, but entire single pulse I am dividing into multiple pulses using a pulse width modulated control based input to the gates of the inverter. So that if I take average value of this, because this is also symmetry waveform, for entire waveform, if this value of average output voltage is 0, so that for half cycle only I'm considering to take the average output voltage of this. So that if you see that the pulse, here we have a maximum value up to this, and here it is 0. Again, maximum value for this pulse width for this period, and it is 0, and for this period it is maximum value, but for this period is 0. Like that, for different width of pulses are maintained. It's not a constant width of pulse. So that based on the width of the pulse, if you take average value of this entire half cycle, this is varied. If this now for current waveform, it is look like uh, these two pulses are having same width, and this one is having same width, and it produces some average output voltage. For the next average output voltage, if you want to vary the voltage, you are going to be changing the width of these pulses based on pulse width modulation index, right? So then once the modulation index is changed, automatically this width of the pulses are changed and the average output voltage is changed. So you can have the variable output voltage from this, and variable frequency also you can get Here, by changing entire time period, means that you can adjust the time period of operation for this for full cycle, and you can have the variable frequency. Means that when the VSI is operated under PWM inverter mode, it will produce the variable output voltage, and it is also produce variable frequency. So that a pulse width modulated inverter, PWM inverter, can capable of control voltage and frequency. There is no external control is required. That is saying. But by using this pulse width modulated inverter, we have some advantages. These are the disadvantages for 6-step inverter. As 6-step inverter having some disadvantages, like it produces more losses, and it has also introduces harmonics like 5th, 7th, 11th and 15th harmonics will be produced. All these harmonics are reduced by operating VSI in PWM inverter mode. This is saying that advantage. This is a disadvantage for that. More harmonics are produced in 6-step inverter. And it also introduces losses. 6-step inverter is having a lot of losses in it uh, during the conversion process, because it is using external controls, external converters to control. This converter loss is also there. So losses are increased. Here external control is not required. The losses are reduced, so that it is advantageous than the 6-step inverter. And it also gives a smooth motion is obtained at low speeds. Uh, because some low speed operations will give some disturbed operations for the 6-step inverter. So here it's a smooth control is there for that also at low speeds operation of the induction motor using PWM inverter. Now the same explanation I also can give here when my available supply is DC and 3-phase AC. If available supply is DC, directly I'm giving this fixed DC to here PWM inverter. Why? Because this PWM inverter internally can capable of control the voltage and frequency. No external control is required. But this fixed DC supply I am processing through the filter, because DC directly is not available. Every DC quantity is converted from AC. So definitely it is a pulsating DC. Hence I am processing that through a filter. So this filter ripples out the ripples in the DC supply, and after rippling out the DC supply, then the ripple out DC supply, I'm connecting it input of the inverter. This is a fixed DC again. And this fixed DC now converted into variable AC and variable frequency, variable voltage. Variable AC supply as a variable voltage and variable frequency. So variable voltage will be getting based on adjusting a modulation index and pulse width of the PWM inverter, and variable frequency we are getting by adjusting the time period of the PWM inverter, so that your induction motor will operate in constant V by F control mode without any external control here PWM inverter. Now your circuit is size and the volume also reduced. That is also an advantage for this compared to the 6-step inverter based. For 6-step inverter based control, we are keeping here it is a chopper circuit. But is a chopper circuit is not required when you are operating the VSI under PWM inverter mode. And another circuit when 3-phase AC is available. And here I need a DC input for the inverter. This is also fixed DC and enough. No need of any controlled DC. Fixed DC is enough. Control voltage will be happens inside the inverter itself. No need of external control. So that I'm using a diode bridge rectifier for reducing the cost. Previously, I used a 3-phase control bridge rectifier here. So now I'm using diode bridge rectifier to reduce the cost, because diodes are very less cost compared to the thyristors. So this AC supply, 3-phase AC supply is converted into constant DC here, fixed DC supply using diode bridge rectifier. This fixed DC is the pulsating DC. It is processed through a filter in order to remove the ripples in the DC supply. So then after rippling out the DC supply here after the filter, and that fixed DC again connected across the PWM inverter, and now PWM inverter can control the voltage and frequency internally. Voltage control is happens by adjusting the width of the pulse. Frequency control can be done by adjusting the total time period of the waveform. Variable voltage and variable frequency of AC is available here, so that we can control this induction motor under constant V by F control. So these are the four possible configurations for VSI to be operate the three-phase induction motor under V by F control, and operating this VSI in two modes like 6-step inverter and PWM inverter modes. Thank you very much.